All right, so rate of change function, called a derivative, as in derived from another function. So if I'm talking about the derivative of function g, I get this derivative from using function g. And that's a term that's frequently used, but all it just means is the derivative of a function is come to mean in mathematics the rate of change function for something. So you can derive all sorts of other related functions from a function you start with, but the derivative in math refers to the rate of change function, which there's many ways to write a rate of change function, but there's usually a simplified closed form, and that's when we're talking about the derivative. Like one particular form of it would be maybe simplified, but anything equivalent to that is also called a derivative. So there's several different notations. I think we talked about this right at the end of class on Tuesday. We've been using the function notation that we're using all along, an R with a subscript, to indicate the rate of change of the function name in the subscript. But there's several other notations, and just talking a little bit about these are things you'll see in a variety of different textbooks, sometimes in our textbook. Like every book uses 2 or 3 of these interchangeably when they're talking about derivatives, and also in addition to ours that we've been talking about all along. But this first one, the d over dx, and then g of x off to the side, that's kind of like our dy over dx, only just since g of x is an unwieldy sort of expression instead of y, it's just off to the side. So thinking symbolically, like as if like this g of x here is over 1, it looks kind of like it's multiplication or something. This is just pulled off to the side to talk about the rate of change of g of x with respect to x. So the second one also, this is a quick fast notation. It's easy to miss a little mark like that, however, so sometimes we won't use that just so you don't miss the fact that we're talking about the derivative. It's read as g prime of x. And then this expression here is just what we've been doing in how we formulate a rate of change function. Take two values of a function that are h units apart, and then imagine h approaching 0, or imagine h being essentially 0. It can't equal 0, because that wouldn't have any meaning, in addition to fractions not having any values. But as we imagine h getting closer and closer to 0, we can see what the trend is in not only numerical values if we were working with a specific spot in a function, not in general x, but also what the function type would be like with x's in there, not just numbers. Yeah. As long as you remember that h needs to be essentially 0, then yeah, this r sub g of it, because that's part of our definition of it, r sub g of x, like this, we always put the with h approximately 0 or h essentially 0, something about that at the end of it. This expression on its own, just this fraction, that wouldn't necessarily mean a derivative. It could just be an approximate rate of change if h were 2 or if h were 0.5 or something, because that doesn't have any meaning on its own other than just change in 2 dependent quantities divided by the change in the corresponding 2 independent quantities. So this could be any dy and dx of any size in reality. But if we say h is essentially 0, then we can say that this is an exact rate of change function in closed form, because with h essentially 0, generally there's a way to not have to write the h, because we can see what it's tending toward as h approaches 0. So these are all, regardless of what notation you see, they're all talking about the rate of change of function g with respect to x, or the rate of change of g of x, the dependent quantity, with respect to x, the independent quantity. So all of them mean that. Oops, and let me scoot this kind of out of the way here, maybe. There we go. So suppose we're going to talk about some different sorts of functions. We talked about x squared and 4/3 pi x cubed the other day, but what if I have a constant function, meaning my accumulation is a constant value, or there's actually nothing accumulating, like function f of x equals 7. Very boring. Nothing accumulates. If I want to talk about the rate of change of something like that, where nothing's accumulating, what is it? Yeah, 0. All right, so just concept-wise, that should make sense. If something has a constant value, I want to know at what rate it's changing. You can say it's not changing. It's changing at a rate of 0 y's per x, whatever the meaning might be. So like the depth of the snow outside, maybe it's like 6 inches, and it just stays that way because it's not snowing. The rate of change of the snow is 0 inches per minute, per hour, per whatever you want, 0. So anything that's remaining constant has a rate of change of 0. So if I wanted to prove that using or see what that means relative to our computation formula, that f of x plus h sort of method, if I were to write, okay, so f of x, let me say it's c. This is constant instead of 6 or 7 or whatever. Let's say I said f of x is the function c, where c is some constant value, any real number. It could even be an imaginary number. If I look at the rate of change of function f, think about the numerator here. F of x is c. What would f of x plus h be? C. So I'd have c minus c all over h. I don't even have to imagine h being particularly small. If the numerator is 0, as long as the denominator isn't also, which it's not, it just can get close to it, then I have a fraction whose value is 0. So that's 0 over h, and as long as h isn't equal to 0, this has meaning still. But regardless, if I let h get closer and closer to 0 or not, this fraction is equal to 0 the whole time. So this is 0, and so the rate of change of a function of this form, f of x equals c, is 0. Or notation-wise, and I turned off my little scribbly tool here a second ago. Notation-wise, let's see. No, doesn't want to work for me today. Let's see if it'll work anyway. Nope. I can say that the rate of change of function f is 0. I could say f prime of x equals 0. I could say that d over dx of c, or of f of x, equals 0 if f of x is this constant c. And it could actually be a number like 3 or 7, but this is just talking about, in general, for any constant value as an accumulation function, the rate of change of that is 0, which should make sense conceptually, but algebra works out too. All right, so constant multiples of a known function. So suppose that at noon, John started biking, Mary started walking, and at every point in time since noon, John's traveled 5 times as far as Mary. So if we're mapping out their distances traveled, whether they're traveling at varying speeds or constant speeds, so I don't have to come up with a formula for it, however far Mary's gone, John's gone 5 times as far. So how is his speed related to hers at any point in time? It's always 5 times as fast, right? So if we're measuring in miles per hour or feet per second or meters per minute, whatever sort of units we're imagining for this computation, if one distance is always 5 times as far as the other distance at every point in time, I don't know what the pattern of these distances are, but if one person's always traveled 5 times as far as the other while they're moving, then the speed of the one must be 5 times the speed of the other. So if I use f of x for John's distance after, and I had to pick units, I'll say after x amount of time has gone by, let's just say it's minutes, and g of x is Mary's distance walked after x minutes, and I want to talk about these two functions, how they're related to one another. According to the paragraph above, f of x is always 5 times g of x. So they started at noon, so I'd only use x values that correspond to, something that's after noon, since they've been moving. But f of x would be 5 times g of x. And so just sensibly speaking, it would have to be the case that his speed is 5 times hers, so the rate of change of f would have to be 5 times the rate of change of g. And I don't know what either of these two functions are. But just based on that scaling factor of 5 that goes from one distance to the other, like we were talking about with parabolas and stuff that you learned in an Algebra 2 class probably back whenever ago, that scaling factor, or that coefficient, magnifies in this case, since it's a large positive number, magnifies the dependent quantities. And so that corresponds to a rate of change dependent with respect to independent, y with respect to x, that's 5 times as great as it was before. So whatever the rate of change of function g and function f are individually, I know that the relationship between them is that the faster one, in this case f, is 5 times the rate of the slower one. So if I know that the relationship between individual functions is this, one function's dependent quantity is 5 times the dependent quantities of the first, then the rates have that same ratio between them, which means that, in general, this looks like a bizarre rule, because I don't know what f is and I don't know what g is. But if you have any function that you know how to find the main underlying properties of x, like x squared, we talked about that. We found the rate of change function for x squared, f of x equals x squared. It was 2 times x, that area of a square computation that we were working with. Well, if I have 5x squared, or 7x squared, or 9x squared, or negative 2x squared, according to this rule here, the rate of change of those functions would be 5 times 2x, or 9 times 2x, or negative 2 times 2x, or whatever numbers I said. But it's just, if you have a constant multiple of a function whose rate you know how to find, then just multiply that constant multiple on to the rate that you found. So this is not just true with 5s, it's true with any constant multiple. So thinking about other ways we can combine things. We haven't done any addition or subtraction sort of things yet, but if I have a function and another function and I add them together, like x squared plus 2x. Well, if I know how to find the rate of change for f of x equals x squared, and maybe I can figure out how to find the rate of change for f of x or g of x equals 2x, constant rate of change of 2, I do believe, right? Then we should be able to somehow use those to find the rate of change function for a sum of those two. So if I have a sum of two known functions, just thinking about, well, what's our rule? What's our trusted rule for how do I find rates of change? F of x plus h minus f of x all over h, and then imagine h essentially 0. Well, this time our function overall is called k of x. So I'd use k's in that expression, but k of x plus h would be, oh, well, here's the rule for k of x. K of x plus h would have x plus h's in those two spots. K of x would just be f of x plus g of x. So although I'd have a kind of messy expression here, it's just a bunch of addition and subtraction in the numerator. And I can't, in general, with generic f's and g's like this, I can't cancel out like terms. There aren't any computations I can see like terms for. But if I rearrange this a little, so I've got 2 positive terms and 2 negative terms. Let me put them together this way. I've got an f of x plus h and a negative f of x. I've got a g of x plus h and a negative g of x. If I kind of separate those out, that numerator looks like just numerators of 2 separate fractions. Because of how we add fractions, I could pull this back apart and make 2 separate fractions, each one of which is exactly an expression for exact rate of change. The one on the left is exact rate of change for f, assuming we let h be essentially 0. Same with the one on the right, only for function g. So and I just didn't write the h essentially 0 on here, but as long as h is essentially 0, we normally do that at the end after we've done some computations with specific functions if we're working this out from scratch. But if I have 2 functions added together, or you can think of it as 2 terms of a function that are just added together, like polynomials. This would obviously extend to more than 2 terms, 3 or 4 or 5 or 17,000. I can just find the rates of change of each term, thinking of each as an individual function, separately. So if k of x is defined as the sum of f of x and g of x, then k's rate of change function comes out to be, we just proved it, the sum of the rate of change function for f and the rate of change function for g. So that's good. Doesn't matter if I have multiple terms in an expression or not. I don't have to come up with an entirely new method for performing rate of change computations, if I know how to deal with each of the individual terms, rate of changes separately, I can just add them back together, or subtract. Subtract could be like a -1 coefficient multiplied on. Add or subtract them back when we're done finding rates of change for each individual piece, each of an individual function that's added or subtracted. So far what we've talked about today, constant functions whose derivative is 0, rate of change function for something that isn't changing is 0. And then this is a specific sort of function. These other two are variations on other functions. If I have a function and multiply it by something, the rate of change function gets multiplied by that same something. If I add together a couple of functions and want to find the rate of change for that sum, I just add together the individual rate of change functions. So that's what we talked about today. Now, last class we actually talked about, and the class before, we talked about some exponents, and we talked about x squared, we talked about a 4/3 pi x cubed, and we even talked about a 12 over x plus 2, which was just a translation of the 12x to the -1, just slid to the left by 2 units. So power functions. Let's talk about power functions. Whether it's x squared, x cubed, x to the 17th power, or any integer, any whole number power, we could work these out kind of the same way. And the proof, we're going to kind of do a little bit more than what we talked about just looking at patterns for a couple of examples on Tuesday. Today I want to show a couple more things to think about, why more about this works in general for whole numbers. For other powers, it's not necessarily apparent that this would work. Like if I had x plus h to the 1/2 power, how do you expand that? Can't. Or x plus h to the -2 power. Well, you could expand it in a denominator, but it's a little bit messier. But thinking about just whole number powers for a minute, and thinking about how I would compute that rate of change function, we did this with squared the other day, x plus h squared minus x squared all over h. We ended up with this trinomial as a part of the numerator of our rate of change function. If it had been cubed instead of squared, we did that using GC, but it worked out to this expression, x cubed plus 3x squared h plus 3xh squared plus h cubed. If we did the fourth power by hand, if you're not familiar with the binomial theorem, it takes a little longer, but still, I know that if there's whole number powers, given enough time, you could all do these. You could expand this x plus h to whatever whole number power we wanted, but there's a nice pattern to them. Binomial theorem explains the pattern of the coefficients with combinations and permutations, and you can just kind of see there's nice patterns for how these work out. Second power starts with an x squared, ends with an h squared, and the middle terms are all combinations of x and h. There's only one for this one. It's x to the first and h to the first. Or you can see that there's a descending order of exponents for x and an ascending, increasing order of exponents for h. Same in these others. The coefficients are there's only one other term in the middle. It's a 6x squared h squared, by the way. But we could keep going with this. There's the important parts to think about these, though. If you remember doing that x plus h squared minus x plus 8, x plus h squared minus x squared all over h, the x squared part canceled out, right? So in general, if I were able to come up with some expansion for x plus h to some whatever whole number power I wanted, don't worry about too many of the details in this, but just this is how it generally turns out: descending powers for x, increasing powers for h, and various coefficients, but the ones right next to the end, notice, are the same number as what the exponent was. So these are n x to the n minus 1, just like this is 2xh and 3x squared h, and so on and so on. So if I were looking at this pattern and trying to find a derivative for f of x equals x to the n, I need to have an expansion for x plus h to the n minus x to the n this is what we're doing here, x plus h to the n minus x to the n. If I multiply out that x plus h to the n, this is that messy, it's the whole ugly stuff. Don't worry about too many of the terms inside. Most of them end up not mattering. But expanding that, whenever we expand x plus h to the any power, the highest power term is just the x raised to that power. So x plus h to the n starts with an x to the n, ends with an h to the n, and there's lots of other stuff in between. But the numerator of this has a minus x to the n, which would cancel out that highest power term of x. All the rest are remaining. All the rest also have h's in them, if you remember that from the other day when we did it a couple times. So those cancel out. In terms of the rest of this, we can factor h to the first power, at least out of all of them. If I factor it out of the first term, there's no more h's left. The remaining terms would all have h to some power or another, whether it's the first power, second power, down to the n minus first power after I factor out. And the reason we did that is so that we can reduce, and then we won't even have a fraction anymore, other than these weird-looking coefficients in the middle. But if I reduce out this factor of h, then I've got this polynomial expression, which is 1 degree lower than it started, meaning 1 degree lower than this x to the n was. The highest power here is x to the n minus 1. It's got a leading coefficient of n, which is what the original exponent was. And all the remaining terms past that still have h's in them as factors. So if I imagine h becoming closer and closer to 0, every single one of these other terms, other than the first one, would become essentially 0 because of that factor of h that they all contain. And this one is all h's. Some of them have other things multiplied on, but they all have an h. So if I can make h small enough, all of those other terms become insignificant. And so the tendency of this whole ugly polynomial is that it gets closer and closer to being just the first term. So for small values of h, or imagining h being essentially 0, this x plus h to the n minus x to the n all over h simplifies to something that's approximately nx to the n minus 1. Meaning, and this is just considering whole number powers, because this expansion doesn't work that way with non-whole number powers. But the rate of change function for anything of this power function form, x to the n, so n is a number, and we just use whole numbers, but it actually works for every number. The rate of change function is something that contains a power of x that's 1 smaller than it started, so x to the n minus 1 if the original is x to the n. And it has a new coefficient that wasn't there before. So this original one, this was just a basic power function, not scaled up or down or reflected or anything, just 1 x to the n. Its rate of change function is n x to the n minus 1. If I had something like 7x to the n, well, that's just a constant multiple of x to the n. So we just dealt with how to deal with extra coefficients a minute ago. So I can say that this is the derivative. I can say it's a rate of change function, but it's derived from, as in it comes from, this accumulation function. You can get one from the other and the other from the first. But if f of x is x to the n, then f prime of x, or r sub f of x, or d over dx of f of x, any of those notations that we want to use, come out to be this n x to the n minus 1. So we just let h become essentially 0 from our simplification in order to get that from all the ugly algebra. But when we say this, then we mean our exact accumulation function. So that's adding one more thing to our list of rules. This one is typically referred to as power rule. It's dealing with power functions, because power functions are things of the form x to the n. Although, like I said, the rule actually applies to all power functions, and the pseudo semi-proof thing that we just looked at was only an example with whole number powers. It actually applies to all powers: positive, negative, rational, irrational, fractional, anything you want. So that's what this purple stuff says. Rule is actually valid for all numerical exponents, and to prove it for other exponents, this is something we'll actually do after your mastery test. It uses some kind of advanced derivative finding techniques using logarithms and their properties and some nice tricks that allow us to rewrite things with exponents without using exponents, logarithms. So we'll be able to find the derivatives using other methods that way and rewrite things with exponents so that it's not something that needs to be expanded, so that it's just a constant multiple. All right, so rate of change functions. We have our power rule and our constant function. So these are specific function types, a constant function or a power function. Then we've got the bottom two below this are variations on a function. You can think of that next one as a coefficient. Constant multiple, throw a coefficient on something that you knew before, or a constant multiple onto something you knew before. Just multiply that same constant onto the rate of change function. Or if you have a sum or a difference, which would be a combination of a sum with a negative constant multiple, then you just add together the separate terms. So for examples of using these, so there are other sorts of functions. We'll talk about exponential functions, logarithmic functions, trig functions, inverse trig functions. There's a whole variety of things, even some fancier things called tower functions, where you have x in both the base and the exponent of a function. Those are trickier. But some weird combinations of things as well, besides just added and subtracted. So look at this polynomial here. P of x equals x to the 11th minus 5x to the 4th plus 10x cubed plus 9. So every piece of this polynomial is related to something up above. So I've got terms of this polynomial that are power functions, 3 of them, and then one term that's a constant. And in these terms, I can see that, oh, well, this is just plain x to the 11th, plain power function. This next one I can think of as being a negative 5x to the 4th added on to the previous term. So I can think, oh, I've got a sum. Well, the difference in this case is how it's written, but I could write this as plus a negative, or a negative 5 coefficient on this x to the 4th, a negative 5 constant multiple on that. We've got a positive 10 constant multiple on this x cubed, and well, that's just a constant. So think about what the rate of change function for this, the derivative of function p, would look like. See if you can write it. And you don't have to work it out with the x plus h's, because we have some shortcut rules. If you've worked out the derivative, the rate of change function for this, you should have only 3 non-zero terms. You might have 4 terms written. One of them is a 0. By finding the rate of change for each individual term of this, thinking of this last rule, just finding the rate of change of the individual parts and then adding them or subtracting them back together. So for this first term, x to the 11th power, that's a power function according to our first rule up here. X to the power n has a derivative n x to the n minus 1. What would that turn into for x to the 11th? The rate of change would be 11x to the 10th. All right, and then this minus 5x to the 4th, I've got a coefficient or a constant multiple of power function x to the 4th. What would the coefficient of the next term of this derivative simplify into? Yeah, I'm going to have a 5 and then multiply it on to 4x cubed. or a negative 5 multiplied onto 4x cubed. However you want to think. You can think of it as subtract and keep the subtraction, or you can think of multiplying on a negative. But we should end up with a minus 20x cubed as the next term in that, and then plus 30x squared, and this 9 is 0. So yeah, so I don't have a fourth term. This is if this were on its own, p of x equals 9, that would be an accumulation function that isn't accumulating, constant value of 9. So the rate of change due to this term is nothing. Or if you want to think of it this way, think about things that you did in previous like algebra classes. If you have some sort of polynomial and you graph it, whether it's a parabola or something else, if I added 9 to the end of it, like x squared versus x squared plus 9, that 9 just moves it upward, right? Doesn't make it steeper or less steep or flip it over or anything. It just shifts it vertically, which doesn't change the rate of change of the steepness. The ratio of y changes to x changes. It just changes the location. So this constant tacked on here doesn't change this anywhere steepness-wise. All it does is shift it up from where it would be otherwise. So if this 9 weren't here, this would have the exact same rate of change function, because regardless of the height of the y values. Now, like if I were talking about a distance function and a rate function. Let's say somebody's distance was measured relative to that door, and someone else's distance going the exact same speed was measured relative to this front table here. If I wanted to know the rate of change of them, if they're going the same speed, their rates of change can be the same. They'd be the same distance apart all the time, but they could have two completely different distance functions, like measuring relative to something else, so that they have different distance functions with the same speed. All right, so taking a break from learning new shortcut rules for just a moment, let's go back to what we were talking about, the relationship between rate and accumulation and going back and forth between them. So if I have this function here, kind of similar to the last one, a little messier, z of x equals 9x to the 8th minus x to the 5th plus 1/4 x to the negative 2 minus pi squared. By the way, pi is a constant, right? So if I'm thinking about the rate of change of this function z, this term doesn't have anything to do with it. So I know I can find the rate of change of function z just doing the same sort of tricks as last time. Now, I will say, watch your exponents when you've got negative powers in power functions. Remember, if you're trying to find a rate of change function, you're going to decrease that exponent by 1. So negative 2 becomes negative 3. It's very easy to accidentally put negative 1. But same rules as before, the rate of change of function z, take a second, write it down if you haven't already. Without doing the whole x plus h, just use our power rule along with our what do you do with coefficients in multiple terms and constants rule. Those don't have such cool names. All right, so rate of change function. This one should also have 3 terms that are non-zero by the time we're done. A 72x to the 7th minus 5x to the 4th. And then for the messy term here, I need to do 1/4 times the derivative of x to the negative 2. So 1/4 times negative 2x to the negative 3, and so the 1/4 times negative 2 becomes that negative 1/2 in kind of simplified, written out polynomial form. Now, one just kind of interjection here. For the purposes of mastery test and most of the time in life, you don't have to bother simplifying derivatives as you get them, but polynomial coefficients, kind of nice to, instead of writing multiplication, just do the multiplication. But generally I won't simplify too much. So here's our rate of change function. There's no number from this. This is a constant despite the fact that it's written with an exponent. It's not 2 pi to the first power because pi is not x, pi is 3.14. So this is like 10-ish or something. So our rate of change function can be written like this. I can call it r sub z of x, or I could write z prime of x. But keep in mind, what we can use rates for, or how we can express accumulation if we know a rate. If you remember what we did prior to your last test, we talked about up through approximate accumulation. But right afterward, we started talking about how do I express, even if I don't know how to write it in closed form, how do I express accumulation using an integral? Well, if I have a rate of change given by 72x to the 7th minus 5x to the 4th minus 1/2 x to the negative 3, I know that's the rate of change function for z up above. It's also the rate of change function for lots of other things, because if I hadn't written this negative pi squared here, it would still have this as its rate function. It could have any other constant, but every accumulation function that I can write this way in open form, accumulation from a to x for any a, could be a way to express z. In fact, what it expresses is z of x minus z of a, right? Because this accumulation, due to that rate between a and x, this isn't just a general formula for anything you want. It's an accumulation starting at A and going onward. So how far I've traveled since noon, or how far or let's see, how much money you've earned since last year, or whatever it might be, where A is that starting point in time, or that relative to some point. It doesn't have to be time, but lots of times our rates are based on an independent variable that uses time. So we have an accumulation that occurs over time in a lot of cases. But like I said, this accumulation from a to x could be part of z, but what I know it is for sure, since this is the rate of change of function z, then I know for sure whether I call this something else, capital, whether I can give this a name just all on its own, but I know that since this is the rate of change for function z, then this is the net accumulation between a and x for function z. Or in other words, it's the difference between z of a and z of x. Z of x being the final, z of a being the initial. So I can express changes in function z between 2 points in time, a and x here. X is kind of general. A is a parameter representing some reference point, some starting point of accumulation, although it could be anything. But since I actually know function z's format, I could also write, instead of z of x minus z of a, or writing this expression here to represent how much accumulates due to function z, or due to this rate, how much accumulates in function z between a and x, I could actually write out function z evaluated at a and evaluated at x and subtract. So point is, these rate functions, you can use them to express accumulation in open form. And that way you can change your relative to what, starting at when and ending when, using the integral sign, as opposed to having to do numerical computations. I think you might agree that this expression, although it is open form, is a little bit less tedious than writing out all of this to express the same thing generally. And that's exactly what they do. These two express the same thing. This integral from a to x of 72t to the 7th minus 5t to the 4th minus 1/2 t to the negative 3rd dt means the same as and has the same values for any value of a and x as this long, messy expression here. So it is actually, although it's an open form, it's like, that it feels like it's not done. This succinct form here means all of that. They have the exact same values for any a and x. It's accumulation from a to x, or the net change in the accumulation whose rate is this, between a and x. All right, so let's look at one other example. Here's a accumulation function that we looked at earlier. P of x equals x to the 11th minus 5x to the 4th plus 10x cubed plus 9. So we already did this part A a couple minutes back. But write the rate of change function in closed form, and then use that to write an expression for p of x minus p of a in open form, meaning using an integral instead of writing out p with x's and a's subbed in. And if you think that's easy, look at part C. So we're going to do something else with that. Let's see if I can get this doodad to work. Restarting it. There we go. All right, so rate of change function in closed form, we had this a little bit earlier. I'm going to use the another notation this time. So I'm taking a derivative with respect to x. You're talking about how the output of function p changes with respect to x. Another way this is sometimes written, dp of x dx, it's like dy over dx. Oops, x, swirly there. But typically written this way. Sometimes this notation is also used if it's like an operation form, like find the derivative of or find the rate of change of p of x. But in any case, the derivative of function p of x, like we said before, would be 11 times x to the 10th minus 20x cubed plus 30x squared, right? So this is the rate of change function. I could call it p prime of x. I can call it this. I can call it that. I can call it r sub p of x. Lots of different notations. But if I want an expression for p of x minus p of a in open form, or the net change in function p between a and a general x, that should be our integral notation from a to x. And using our rate function here. Remember that it's an accumulation due to a rate function, so I want m dx sort of expression inside or after the integral. So our m is these three terms. Only I'm going to use not x, since I already have used x once. I'm going to use 11 t to the 10th minus 20 t cubed plus 30 t squared times dt. So I'm letting t vary from a through x at this rate, and that should give me accumulation like p of x, but only from a to x, so it tells me what happens in function p between a starting point a and a general x, so this is final minus initial. So p of x minus p of a in open form would be this. In closed form, I'd have all of that minus same expression with a's in those spots. Now, this expression here, we talked about some expressions that look kind of like this back right after your test, thinking about what defines an accumulation function properly. So this one, I've got some sort of rate times dt, so I can think of an mdx sort of expression, an accumulation that happens from 2 through x at this rate. So if I knew what this was the rate of change for, let me call it r sub g of, well, t, the way it's written right now, then if I knew that function g, whose rate of change function this is, this could be g, oops, I use capital and lowercase kind of interchangeably here. This could be g of x minus g of 2. So question is, can you come up with a function whose rate of change function, whose derivative, is that? Yeah, if you look up above, we had almost the same here. 30x squared, this is 30t squared. 30x squared in this derivative came from 10x cubed in an accumulation function. So thinking same here, oh, well, g of x then could be 10x cubed. That would be the g of x part. I need g of 2 also, so I'd need 10 times 2 cubed, or 80. So I've got 10x cubed minus 80 in simplified form. But this expression then would be accumulation due to rate 30t squared happening from 2 through any x would be given by this expression here, this 10x cubed minus 80. Try the same with number 2 if you didn't quite get what was going on in number 1 there. See if you can take a good guess. Now, there's not an exact, it's right up above, but maybe take a guess at what would be the accumulation closed form that we would need to come up with. And then I want to mention one other thing. Change colors here. So let me call this r sub f of w. Yeah. Oh, so the open form is this sort of integral, meaning there's infinitely many different operations, like we're adding up infinitely many mdx's between 2 and x. So this is considered open form. This and this other one here are also, those are considered closed form, just exponents. This is just simplified and unsimplified, but that's kind of an in-between kind of describing what's going on, but we need to come up with the function g of x, or in the case of this one, oh, I wrote w. That's silly. Don't want w. W is the variable that was used. F is what I said. So if I call this r sub f of w, then this would be f of x and f of pi is what we need. Yeah?
Do you have to have a starting value for this? Like, in the event that it's an integral from, like, a to x, can you solve it? Or do you have to have, like, the...
Oh, if it was just the symbol a, I could write it with a's in here. So this would just be 10a cubed instead of something that I could simplify. So if it has a parameter in the description, like some general constant to start at instead of a specific constant like pi or 3 or something, we can still write it in closed form. It's just going to have a parameter still. So this number 2 here, just to have something to call it, let's say that that rate function that's in the integral, the rate of change is r sub f of w, meaning it's the rate of change of some mystery function f. What has to be in that mystery function f in order for this to be its rate of change? Let's say if I call it f of x, aside from the letter x somehow being a part of it, what would have to be in function f? Hint, it's a power function. Yeah, x to the 29th? Yeah, if I had x to the 29th power, and I asked you to find the rate of change of this, using power rule, I'd have 29x to the 28th. This is just different independent variables used, placeholder sorts of things. But f of x could be x to the 29th, and f of pi would be pi to the 29th, which I'm not going to multiply that out. But here would be a closed form version of that. Now, the one other thing I wanted to mention, we talked about a little bit earlier today, there are a whole bunch of different functions that can have the exact same rate of change. In reality, when you're doing these problems, it doesn't matter which one you use. So what I mean by that is, this 30t squared as a rate function could have come from just something like, well, let's say it's 30x squared. So if 30x squared is the rate of change for some function f, the original f function could have been, like we used, let's see, what do we have? 10x cubed. But just like this 9 added on here doesn't do anything to the rate of change function, I could have had another option here. F of x is 10x cubed minus pi to the pi to the 7th power. Or it could have been f of x equals 10x cubed plus 93,000. There are infinitely many options, but the only difference between them is, you know, if there's some constant or another. So that would all be, that's something that you can't know from just looking at the rate. Like, I can't tell how far I am from this table in the front of the room just based on how fast I'm moving. I would have to have some other given information, y initial sort of information. But that doesn't affect our ability to answer these problems. So let's say that for whatever reason I knew something about the function. I know it was actually 10x cubed. Let me make something easier. The original function was not just 10x cubed, it was 10x cubed plus 19. Well, if I evaluate that at 2, that's 10 times 2 cubed, 80 still, plus 19. So when I subtract the two of them, both halves of the subtraction problem have just been increased by 19, so the difference is still the same. That's why we don't, there's infinitely many different functions that have the same rate function, but to answer these sorts of questions, it doesn't matter which one we use. We just have to come up with one of them. If you can come up with any accumulation function that has the given rate in the integrand, then you can solve these problems one just as well as the other. Now, if there is additional given information, again, we'll do this maybe next class. If there's additional given information, then you can figure out, oh, the original function whose rate we saw, here's what the starting value was, or here's some y initial. But this, we didn't have any knowledge about it. All we had to do was come up with some sort of initial value, or some sort of accumulation function. Doesn't matter which initial value you imagined, or if you imagine it 0. So where we're going next, as I said, we're going to talk about, and I'll just save this for next week, a good place to stop, but we still have some other things to talk about, namely other sorts of functions. We've talked about polynomials by way of power functions with coefficients and adding or subtracting things together, but there's things like exponential logarithmic functions, trig functions, and then there's also issues like, although it just really involves polynomials, if I had a rational function, like 2x plus 3 over x squared minus 4, well, those have asymptotes and stuff, so it can't be just as simple as take the derivative of one polynomial, take the derivative of the other, and divide them. Unfortunately, multiplication and division are a little messier than adding and subtracting, But we have rules for that, and I'm going to assign you to look at rules over the weekend so that we'll see them on Tuesday, and they'll look more familiar by then, called product rule and quotient rule. We're also going to do something called chain rule, which is less obvious what that is, but it relates to compositions of functions. So we could take a derivative of a square root of x, but what if it's a square root of a polynomial, like square root of x squared plus 5x minus 14? So it's kind of, there's a polynomial, but then there's also this other power function, a power of a power. I don't know how to take that square root. So we'll deal with compositions of functions also. And all of this is coming over the next couple of weeks. We'll finish most of it next week and then just kind of work on a lot of practice the following week so that by the week after that, you're ready for your mastery test. And you will have all had many recitations where you're doing some practice towards your mastery as well. Mastery test, as I sent in an announcement, but I had a typo in the original. I fixed it in the announcement. It doesn't resend it. Wednesday, October, which is 30th. Wednesday, October 30th, because there's a shortage of rooms on Tuesday nights on campus. There aren't any that can hold more than 30 people. So Wednesday night from 4 to 7 in Education Building C, EDC, room 117. Big, huge room. It's the other side of campus. Yeah, it's that way. What direction am I facing? It's on the west side of campus, closer, well, all the education buildings are kind of in the same place. Find a map, check it out. It's a little bit south of here as well, I think. But I will see you multiple times before that. In the meantime, if you're wandering around campus, see if you can find building EDC. I haven't been there in multiple years, so I'll see if I can find it too. All right, I will see you next week.